Okay, let's talk about the butterfly effect. We all know the gist, right? Some tiny little action ends up causing these huge unexpected consequences down the line. But what if I told you the way we all think about it, the version from the movies? It gets the single most important part of the science completely, totally backward. Let's get into it.
I mean, this quote from Jurassic Park is pretty much the perfect summary of the idea, isn't it? It's how pop culture has defined this whole concept for us for decades. A single, tiny, identifiable cause, the butterfly's wings, triggers this massive, distant effect, a change in the weather. It's a great story, but it's not the real story.
So, to really get to the heart of the science, we first have to kind of dismantle the myth. By really looking at what the butterfly effect isn't, we're going to see why the truth is so much more interesting.
Right, so this is the formula you see everywhere, like in Ray Bradbury's classic story, A Sound of Thunder. A time traveler steps on a butterfly millions of years ago, and when he gets back to his own time, everything's changed into this awful dystopia. In these stories, the cause is super specific, and you can trace the chain of events. It's all about a cause and effect that we can, at least in theory, follow. Okay, and here's the big twist. The entire scientific point of the butterfly effect isn't that we can trace the cause, it's that we absolutely, fundamentally cannot. It's not a story about one single butterfly. It's a story about the impossibility of ever knowing which of the countless, tiny, invisible factors was the one that tipped the scales. The real idea is all about unpredictability, not traceable cause and effect. So, where did this radical idea of unpredictability come from? Well, the true story is just as fascinating as the fiction. It all starts back in the 1960s, not with a sci-fi writer, but with a meteorologist at MIT named Edward Lorenz, and a happy little accident with a very, very slow computer. So, back in 1961, Lorenz is running this super complex weather simulation. To save some time, and these things took forever back then, he decides to restart a run from the middle. So he types the numbers back in from a paper printout. But here's the thing, the printout rounded the numbers off. And the result? It was shocking. The new weather pattern completely diverged from the original. It was a total accident. And that catchy name? That didn't even come along until a decade later, when a conference organizer basically made it up on the spot for a title. And just look at how small this mistake was. The computer was working with 0.506127, but Lorenz typed in 0.506. I mean, that difference is minuscule. Back then, any scientist on the planet would have told you that was a rounding error, completely irrelevant. But in his simulation, that tiny, tiny change led to a completely different long-term weather forecast. It blew his mind. Turns out, this wasn't just some computer glitch. What Lorenz had stumbled upon was a fundamental property of how certain systems work, and it kicked off a whole new field of science dedicated to understanding this beautiful, hidden order we now call chaos theory. So the official, the fancy scientific name for the butterfly effect is sensitive dependence on initial conditions, or SDIC for short. It's a formal property of what scientists call chaotic systems. All it really means is that any two starting points, no matter how ridiculously close they are to each other, will eventually produce futures that are completely different. And this isn't just a metaphor, it's a mathematical fact. And this is the really cool part. When Lorenz graphed the equations from his weather model, he didn't just get a bunch of random squiggles, he discovered this beautiful, intricate, hidden order, a shape now called the Lorenz attractor. And in what has to be some kind of cosmic poetry, this abstract map of chaos looks, well, it looks an awful lot like the wings of a butterfly. Now, for mathematicians to call a system truly chaotic, it needs a little more than just that sensitivity we've been talking about. It also needs these other two properties you see here. And they basically just mean that the system is really well mixed and that it has this incredibly deep, hidden structure of repeating patterns. We won't go deep on these, but just know that these three pillars are what build the whole architecture of chaos. Okay, so this isn't just some abstract math puzzle. Chaos theory has some very real, very tangible consequences for everything, from the weather forecast on your phone to the ultimate fate of our entire solar system. Ever wonder why we can't get a reliable weather forecast for a month from now? Yup, it's the butterfly effect. Because our atmosphere is a chaotic system, there's a hard physical limit to how far out we can accurately predict the weather. And most scientists put that limit at about 2 weeks. Anything beyond that, and a supercomputer's forecast is basically no better than just guessing based on historical averages. So how do meteorologists deal with this? Well, they don't try to fight chaos. They embrace it. It's a method called ensemble forecasting.
Instead of running one simulation, they run dozens, maybe hundreds, all at the same time. And each one starts with slightly different data, just to account for tiny measurement errors. If most of those simulations end up looking similar, the forecast is pretty confident. If they all fly off in different directions, well, the forecast is uncertain. That 30% chance of rain you see on the news, that is the butterfly effect in action.
This brings us right back to the core idea. Let's call them butterfly effect 1 and 2. The real science, BE1, is that tiny uncertainties everywhere, all at once, make the system as a whole unpredictable. The Hollywood metaphor, BE2, is that one specific butterfly causes one specific tornado. Physicists have actually shown that's pretty much impossible. The tiny bit of energy from a real butterfly's wings would just dissipate as heat long before it could ever grow into a storm. And get this whole idea is way older than you think. The first person to really catch a glimpse of this deep unpredictability wasn't Lorentz at all. It was a French mathematician named Henri Poincaré, all the way back in the 1880s. He was trying to prove that the solar system was stable and predictable forever. Instead, he discovered that the gravitational pull of just 3 bodies could be so complex that even the tiniest errors in measurement would make long-term prediction impossible. That's right, our own solar system is a chaotic system.
And that discovery, it didn't just change math. It completely shattered a scientific worldview that had stood for centuries. And it forced us to rethink some of our most basic ideas about how the universe works and what we can actually know about it. See, for hundreds of years after Newton, everybody pretty much thought these two ideas were the same thing. They figured that if the universe was deterministic, meaning the future is already set in stone by the past and the laws of physics, then it must also be predictable. It seemed obvious. If you know the starting conditions and you know the rules, you can calculate the end. Well, chaos theory is what finally drove a wedge right between them. And here it is, maybe the most profound takeaway from all of this. The butterfly effect proves that a system can be perfectly deterministic, following exact, unbreakable laws, while also being completely and fundamentally unpredictable. It shows us a universe that runs on unshakable rules, but is still capable of infinite creativity, surprise, and novelty. Now, it's really important not to get this confused with quantum uncertainty. They're different things. The unpredictability and chaos comes from our ignorance of the starting conditions. If we could know them perfectly, we could predict the future. But in the quantum world, uncertainty is fundamental. Reality itself is built on probabilities. And what's really wild is that quantum mechanics, which is governed by simpler linear equations, actually tends to suppress classical chaos at the smallest scales.
So we're left with this absolutely fascinating picture of our world. A universe that follows strict, unbreakable laws, but whose future can never be fully known. It's a universe of perfect order, but also one of endless surprise. And that leaves us with one final thought to chew on. If the story of the universe is already written, but it's impossible for us to ever read ahead, what does that really mean for our idea of destiny? Thanks for listening.